Hi, this is the first part of two parts of video of showing a sample and return with the PSoC5 implementation. This is going to be in part of the development for the logic analyzer. So, if you look at the top design of the PSoC5, it has these input-output pins right here, which are just set up as high-impedance digital pins with a threshold of half the input-output voltage, which is 5 volts. So, threshold is 2.5 volts. There's a couple main components. There's USB UART component. There's a DMA buffer, an ISR, and a clock. The clock runs and sends requests to the DMA buffer to go out and move data from the port 12 pin state register to another array specified inside the code. Once that is done 1,000 times, meaning 1,000 bytes have been moved, signal is sent to trigger the ISR, and the ISR will come out of that and tell the PSoC to now send the data back up to the PC. If we look at the pins, basically the 12 input pins are all mapped to the 12 special input-output pins. Pin 9 is an LED that actually didn't get used in this, and USB UART is set to the USB pins. If we go to the main file, we can see a couple things. I've set the buffer length for each USB package to be 64. I've set the sequential buffer length to be 1,000. Numbers can change. The code is flexible enough. A couple trackers to keep track of where I'm in counting data and where I am transmitting data, and a DMA done flag. So this is the USB bolt transmit. What it does is it goes through the 1,000 buffer sequential and breaks it up into 64 or however many I want until the end of time and keeps sending data. And once it's done sending data, it changes the logic analyzer state to idle. Actually, let's go look at those. Here's a couple definitions. Basically, the logic analyzer has four states: idle, wait, read, transmit. I use idle, read, transmit in this. Wait is for waiting for interrupts on a pin to begin sampling, but that's not implemented in this. Read just means the logic analyzer should start reading the signal. Transmit means it should be sending the signal. Idle means it's just doing nothing. Back to the main code. This is the receive processing. It happens whenever a receive packet is received from the host computer. It breaks out in a case for USB start, stop, config, and what it does. Looking down, the sample clock is turned off just as a safety measure. You've got buffer in, buffer out, buffer data. Those are all for the datas. Buffer in, buffer out are the USB UART in and out buffers. Buffer data is where the buffer is held by that. This is the setup for the DMA engine. The DMA engine will set itself up to read the port 12 pin state register and send it to the buffer data right here. The ISRs, the interrupts are turned on, the ISR is turned on. The USB is started in 5 volt operations. Wait for it to enumerate, and then initialize it, and then start the clock. Once the clock is started, and when the DMA is enabled, then it will do that. Right now, the logic analyzer starts in sequential mode, which is the only mode I have right now, and idle. So the while loop is just if statements. Basically, an if statement for a DMA done flag, an if statement for a USB UART package received, and an if statement for anything other than idle. So the code will churn until it receives a package, basically. And then it will go up to the package and see. For instance, what I'm going to do in the second video is send it a start command. Start command sees if it's in sequential mode. If it is, it sets the logic analyzer state to read. Goes down to read, which is down here somewhere. Oh, here it is. Logic analyzer state to read. That just enables the DMA. Once the DMA is enabled, it keeps doing that and doing that and doing that until the ISR till 1,000 bytes are processed and the ISR trigger is set. The ISR actually sets the DMA done flag to 1. Once the DMA done flag is set, the DMA channel is disabled. The DMA flag is set to 0, and the logic analyzer state is to transmit. Once it's in transmit, it goes to USB bulk transfer and tells it to send all the data it needs to. It sends 64 bytes every time this is sent, and it just continues to repeat as this flag is continued to hit up here until the process is done. Like I said, the second video will show this actually working with me sending to the terminal, and this is just an explanation of the code and how it works.